Alright, in number 58, we are trying to find the inverse function of f. Another way to write f of x is that it is equal to y, right? So what we can do when finding an inverse function is switch the values of x and y. So I can say instead of y equals x cubed plus 2, I can say x equals y cubed plus 2. And then I work my way using inverse order of operations to solve for y. So I subtract 2 from both sides of that equation, find that it is equal to, that x minus 2 is equal to y cubed, and then therefore y is equal to the cube root of x minus 2. So our inverse function is equal to the cube root of x minus 2. Number 59. Remember that e is a number that is approximately 2.7 something something. So in our minds for right now, let's just say that e is a number that's pretty much close to 3, right? So this function, not for all values, but we can think of it in a way as acting similar to 3 to the x plus 3 to the negative x. Also with negative powers, we can think of this as 3 plus, remember that if we have a negative power, we find its reciprocal and raise it in the same magnitude for the exponent. So this function is very similar to 3 to the x plus 1 over 3 to the x. It would look almost the same. So if x is greater than 0, right? First off, if x is exactly equal to 0, we would have 3 to a 0, which is 1, plus 1 over 3 to a 0, still 1 over 1, which is 1. So in our final composite function, we would have this equal to 2. If it were e to the x and e to the negative x alone, this value here and here would both be equal to 1. I draw a little line here. I shouldn't have that little line. Okay, so if f is, let's say, greater than, or excuse me, if x is greater than 0, right? Let's say x equal to 2. We would be adding 3 squared plus 1 over 3 squared, right? So this would be 9 plus 1/9, right? 9 is much bigger than 1/9. That's easy to see. And as the exponent gets even larger, right, we would have, let's say, 3 to a 300th plus 1 over 3 to a 300th. Clearly, 3 to a 300th is much, much bigger than 1 over 3 to a 300th, right? So what we're getting at here is that if this is e to the x, right, for x greater than 0, we have the function that looks like this, right? And e to the negative x is a function that looks like this. As x is getting bigger, e to the negative x is getting much, much smaller. So for very big values of x, e to the x, we say, dominates, right? Because the numbers in the first term are much, much bigger than the numbers in the second term. So e to the negative x plus e to the x for x greater than 0 would look almost exactly like e to the x. On the other side, so let me erase some of these things, some of these scratch notes that I just made. On the other side, for x less than 0, we would have 3 to a, let's say, negative 2 plus 1 over 3 to a negative 2. And it's well, not surprising, but the roles of the first and second term become reversed. So we have plus 3 squared, right? Because if we have a negative exponent in the denominator, it gets the reciprocal becomes, we would put it up in the numerator, right? And same thing in the first term. It would become 1 over 3 squared. So, in this instance, our graph of e to the negative x would dominate because the values in the second term would become much more than the values in the first term, right? And e to the negative x for x less than 0 looks like this. E to the positive x looks like this, but our e to the negative x would become the thing that we would predominantly see. Okay, let me erase some of these. So our final graph would look like what we have located right here. All right. Next problem, number 60. Okay, we have solve the equation natural log of x equals natural log of x plus 2 minus 1. All right. So one thing that we can do is, if we have two natural logs and we want to figure out what's inside of them, we can raise it to the base of the natural log. So you have to know from pre-calc that e to a natural log of x is just equal to x, or whatever is inside the natural log. So here we have, if we take e to a natural log of x, we get out x. On the other side, we can't explicitly do this just yet because we don't have e to just the natural log of something. We have e to the natural log of something minus 1. So first we have to deal with this minus 1 term in the exponent. We can do that because if I have e to the x plus y, or more precisely, if I have e to the x minus y, it is equal to e to the x times e to the negative y. Because if I have two powers multiplied, or two bases multiplied, I would add the exponents together, right? So the reverse is also true. So I can take this negative 1 and split it up so that I have e to a natural log of x plus 2 times e to a negative 1. And then e to a natural log of x plus 2 is just x plus 2. I can distribute this e to a negative 1 to both terms inside this quantity. So, and then I believe that I subtract e to the negative 1x on both sides, so I would get x equals e to the negative 1x plus 2x, and then I subtract e to a negative 1x from both sides, minus e to a negative 1x, and I get this. And then I factor out x from both of these terms, and I get 1 minus e to the negative 1 quantity times x equals 2 to a e to a negative 1. Therefore, I divide both sides by this to solve for x, and I get x equal to e to a negative 1 divided by 1 minus e to a negative 1. You could leave it like this, and this would be correct. If you wanted to get rid of some of these negative exponents, you could multiply it by an e over an e, same thing as 1. So on the top, this would become e to a negative 1 times e just becomes 1. And distribute e to both of these terms, and we would get e minus 1. And this expression here, this fraction, is a little bit simpler